Hello and welcome to today's video. In today's video, we're going to be going over topic 5.2 and Riemann sums and definite integrals. So I really just want to highlight the importance of Riemann sums, really, and just take a bit more time explaining them and why they work. Riemann was a revolutionary mathematician of his time, being born in September 17th of 1826. So he's actually a lot more newer to the calculus game than a lot of the previous people we've talked about, like Newton and Leibniz. So while previous mathematicians have discovered ways of finding the area under the curve, primarily dividing it into smaller polygons, Riemann really generalized this by using a infinite amount of rectangles, or an amount of rectangles, so we can get a approximation within error of our choosing, to really allow us to approximate this area under the curve. So there is really three kinds of sums that I wanted to talk about. And those types of sums are the left-hand sum, the midpoint sum, and the right-hand sum. Now suppose that I want to find the area under the curve from A to B on this interval. Okay. Well, we have three different ways of approaching this. In fact, there's an infinite many ways, but these are three major ones. Well, let's say I want to use a left-hand sum. Well, what is a left-hand sum? A left-hand sum supposes that we use the left endpoints of the interval. So we're going to divide this into n intervals. So we'll say that this is x of 1, x of 2, x of 3, and so on until we eventually reach x of n and x of n minus 1. So what the left-hand supposes, or the left-hand sum supposes, we're going to use the left endpoint of every interval and then multiply it by this very small width change in x, which is the change in x is equal to the endpoint, or the higher endpoint of the interval minus the lower endpoint of the interval, divided by the amount of rectangles, and that's going to give us our change in x. So we're going to multiply the value of f of x at the left endpoints times by these change of x's, and that's going to somewhat look something like this. And you're going to notice that there's going to be a very small bit of area left out from these curves. Alright, the next way that the next way of approximation I would like to talk about is the right-hand sum. I know I'm kind of skipping over the midpoint sum, but I feel like it's important to really understand where it's coming from. Well, the right-hand supposes we have the same n amount of subintervals, so we still have like the x of 1, the x of 2, the x of 3, all until we reach the x of n minus 1 and then x of n. Well, instead of using the left endpoint on these subintervals, we're going to be using the right endpoint, or the higher of the two. So we'll be using b, x of n minus 1, x of n minus 2, x of n minus 3, x of n minus 4, until we eventually will reach x of n, or x of 1. Then we'll be multiplying the heights of all of these intervals times by the width. So it's really whatever this value f of the end point of the interval, so x of n, or f of x of n minus 1, and we're multiplying it by the width. Alright, and then finally, we have the midpoint. So we have the exact same intervals as the left and the right hand sums. So I'm just going to draw this out here, n minus 1, and then x of n. But rather than using the endpoints of the intervals, what we're going to do is use the midpoint. We're going to be using whatever x of I plus 1 minus x of I divided by, or actually, I suppose this should rather be x of, I minus x of I plus, plus 1 divided by 2. Or another way to write this, I suppose, and what might be a bit better understood, is x of I minus 1 plus x of I divided by 2. Either of these two options should work, hopefully, because you're going to be taking, let's say, well, I suppose the left one more or less represents a left-hand sum, and the right one will represent a right-hand sum in the way of writing it. So I'm actually going to erase this first left option for the way of writing it. So now, how do we actually write these sums? Well, for this left-hand sum, it's often denoted as left of n, and this is just saying that we have an n amount of rectangles is equal to the sum from I is equal to 0 to n of f of x f of x not, but x of I times by a change in x. So we're going to be adding, what this really looks like here is f of x of 0, which is really the left endpoint, times by a change in x, plus a f of x of 1, which is the left endpoint of the second interval, plus f of x of 2, which is the left endpoint of the third interval, change in x, and so on. But because we don't have the left endpoint of this last x of n, we just have to go to f of x of n minus 1 times by the change in x. Alrighty. Well, now let's talk about the right-hand sum. Again, kind of skipping over the midpoint sum a little. But what it's going to look like here is we're going to say the right-hand sum with n rectangles is equal to the sum from I is equal to 1, because we're starting with this first x. We're starting with the right endpoint, which in this case is going to be going from x naught to x of 1. X of 1 is the right endpoint, so we start with x of 1 to n. So we're starting with x of I times by a change in x. And similarly, this can be written out as f of x of 1 times by a change in x plus an f of x of 2 times by a change in x, and so on and so forth. But this time, we reach a f of x of n times by a change in x, kind of scrunched there. So you might be asking ourselves, what might we use for this third midpoint sum? And the answer to that is we're going to say the m of n, with m representing the amount of rectangles, is going to be the sum from I is equal to 1 of n. And you can see that this has parallels with the right-hand sum of f of x bar of I times by a change in x, where x bar is equal to x of I minus 1 plus x of I divided by 2. So you can see here that if we're going to say we're adding in the first, or we're adding the first term here, we're really just going to be adding x naught plus x of 1, dividing that by 2, and that's going to be the f of x value that we use. So really, this is going to be written out as f of x bar, here, x bar of I, times by our change in x, but in this case it's x bar of 1, times by change in x, plus f of x bar of 2, plus f of, and let's say dot dot dot, f of x bar of n, times by our change in x. And all of these, the change in x is equal to b minus a divided by n. So now I want us to estimate the area under the curve of y is equal to e to the power of x squared from from x is equal to 1 to 4 using 3 rectangles. So we have 3 different ways of doing this. We can use a left-hand sum of 3, a right-hand sum of 3, or a midpoint sum of 3. And we're going to do all 3 of these. Probably separate these out a little bit so I can have some space. So the left-hand sum of 3 is going to be equal to the sum from I is equal to 0 to n of f of, in this case, f is going to be e to the x squared of I times by the change in x. Change in x for all of these is going to be 4 minus 1. I suppose I should have said equal to 4, divided by 3 rectangles. So we get 1. So expanding this out, we are going to get e to the x of 1 plus e to the x of 2, or sorry, x of 0, x of 1, and then finally we stop with x of, oh sorry, there should be an n minus 1 here, so that should evaluate to x of 2. And I've realized that I misspoke up here. This should be n minus 1. Another equivalent form of saying this is also the sum from I is equal to 1 to n of f of x of I minus 1 times by a change in x. Alright, so now what we have here is, what is these values? Well, what this is really saying is, we want to start with x of naught. X of naught is always going to be the leftmost interval, which in this case is going to be 1. So this is e of 1. Well, to get x, the next interval, we have to add 1, since our change of x is 1. So we'll get plus e to the 2 squared. Alrighty, plus, and now we're adding 1 onto 2 to get the left value of our third interval, and that is going to be e cubed squared. Adding these all up, we're going to get e plus e to the 4th plus e to the 9th. That is kind of messy, so I'm not actually going to evaluate that. Alright, now let's look at the right-hand sum. So now we are going to be going from the sum from I is equal to 1 to n, which in this case is 3. So we're going to be going from e to the x of I squared times by our change in x, which is still 1. Expanding this out, we start now with our first subinterval, or with our right endpoint of our first subinterval, which is going to be e of 1 squared. Then we have to add the right endpoint of our second interval, which is going to occur at x is equal to, I have misspoken. So just I'm going to sketch out this graph here. So we have the function y is equal to x, e to the x squared. We are evaluating it from 1 to 4, and we have each of these subintervals with the width change of x. We're at 2, 3, and then 4. So we're starting at the right endpoint here, which is actually going to be e squared squared. Then we're going to be moving on to our second interval, which is from 2 to 3, and we're using the right endpoint, which is 3. So which is going to be e to the third squared. And finally, we're moving on to our third interval, and we're using the right endpoint, so it's going to be e to the fourth squared. And now just simplifying this a little, we get e to the fourth plus e to the ninth plus e to the 16th. This is without a doubt greater. This is greater than this other function, the left-hand sum. The right-hand sum is greater than the right-hand sum, or the right-hand sum is greater than the left-hand sum, which is an interesting to note. Well, now we're working with midpoints. So it's going to be the sum from I is equal to 1 to 3 of e to the x bar of I squared. So we now have to find the average values of these intervals. Well, 2 plus 1, that's 3. Divide that by 2, that's going to be 1.5. And now from there, we can just add the plus 1 for each interval. So we'll get 1.5, 2.5, and 3.5 for the points that we're going to be using as the height, or to find the height of the rectangles. So we really here will have e to the 1.5 squared plus e to the 2.5 squared plus e to the 3.5 squared. And now I'm going to do a small bit of calculator magic to tell you the approximate values of all of these. So I'll be back now. Now that I have the values here, you can really see and comprehend the fact that the right-hand sum is going to be a overestimate. The left-hand sum is going to be a very drastic understatement, and the midpoint sum is going to be somewhere between the two. So the reason why the left-hand sum is actually going to be an underestimate of the area under the curve is because the curve is increasing. We're always going to have a small bit of area between the height of the rectangle and the value of f of x. The reason why the right-hand curve is a overestimate is because f of x is increasing as well. Well, in this case, there's going to be more area accounted for. The height of the rectangle is actually going to be, for the most part, above the curve. The midpoint sum is going to have some area that is going to be on the outside of the curve, or rather, and some value above the curve. There's going to be some that's above the curve and some that's underneath the curve. And because of this fact, the midpoint sum is normally the best estimate for the function. Well, now that we've done a small bit of work with Riemann sums, let me ask you this. How would you find the exact area under this curve? Well, we're going to be taking the integral from... wait, that's a bit too soon for you. But if we want to find the exact area under this curve, what could we do? Well, let's take a very small trip down memory lane here. When we wanted to find the exact, or the value of the derivative near a point, We didn't know how to do that at first, so we took secant lines, or we tried to find secant lines of a curve, or of a point, to estimate the slope. Well, then we took the limit as h approaches 0 of f of x plus h minus f of x all over h. This led us to being able to find the exact area under the curve. Well, let me suppose this. What if we had an infinite amount of rectangles? Well, as the n gets bigger and bigger, the approximation isn't going to be an approximation anymore. In fact, it's going to become the exact value. So we say the limit as n approaches infinity now, as we're taking n amount of rectangles, of the sum from I is equal to 1 to n of f of x of I times by a change in x, where change in x is equal to b minus a divided by n. This value here is going to no longer be an approximation for the area. It is going to be the exact area under the curve. And as we're going to see in a moment, this is going to be a very big idea. So the definite integral, the definition of it is if a function is defined on the interval from a to b, we divide the interval a to b into n subintervals of equal width, equal to change of x of b, or change in x is equal to b minus a over n. Then the definite integral of f is given by the integral. So this symbol right here is called the integral from a to b of f of x dx. And that is equal to the limit as n goes to infinity of the summation of I is equal to 1 to n of f of x of I times by the change of x. So now we want to evaluate the following integral. Well, what we have to do here is we have to start by changing this into a form we know how to solve. We're going to take a limit as n goes to infinity of the sum from I is equal to 1 to n of 2x, or in this case, we're just going to call this f of x of I times by a change in x. Change in x in this case is going to be the first thing we're going to solve for, because it's going to be the easiest thing to take out in most cases. So we're going to say our change in x is equal to 4 minus negative 1, which becomes plus 1, divided by n. So this becomes 5 over n. So we're now going to rewrite this sum, or the limit as n goes to infinity of 5 divided by n times by the sum from I is equal to 1 to n of f of x of I. Alright, well, now let's expand this f of x of I out. So we're now going to get the limit as n approaches infinity of f of x of 1 plus, 5 over n times by f of x of I plus f of x of 1. There we go. Plus f of x of 2 plus f of x of 3, so on, until we reach f of x of n. Well, we know that f of x of I, f of, or actually I'm going to say this like this, x of 2 or x of n plus 1 is equal to x of n plus by a change in x. So f of x of 1 is going to be equal to the starting point. So this is now equal to the limit as n goes to infinity of f of the starting point, which in this case is -1. Ooh, I chose this to be actually kind of difficult for a starting one, but this should be fine. Plus the first change of x, which is 5 over n. Plus f of -1 plus, and actually I'm going to write this out front just for emphasis, plus 1. Plus 2 times by 5 over n. Plus f of -1 plus 3 times by 5 over n. And we're going to continue this until we reach f of -1 plus n times by 5 over n. Alrighty. Now what do we do? Now we can just evaluate the function at these points, and then hopefully you be able to use some of our summation formulas to evaluate this. So now we have the limit as n goes to infinity of 5 over n times by, alright, we have 2 times by -1 plus 1 times by 5 over n plus 2. And I'm going to have to probably shorten this down to just 2 the second time. Alright. Times by -1 plus 2 times by the 5 over n plus... Ooh, I forgot something. Give me a moment. I gotta move this out. There we go. Plus 2 times this. Because this 2 is a part of this original function. It just doesn't have an x in it, so we don't subsidize anything. Alright, and bracket plus -1. Nope, I'm lying to you again. Plus 2. Alrighty. Now we have to... And we're going to keep doing this until we reach 2 times by -1 plus n times by 5 over n plus 2. Well, we can rewrite this, these extra 2's that are just hanging about, as 2 times by n. So this becomes the limit as n approaches infinity of 5 over n times by 2 times by n plus 2 times by -1 plus 1 times by 5 over n. And we just really factored out this 2 plus 2 over times by n. Plus -1 plus 2 times by 5 over n. And so on until we reach 2 times by -1 plus n times by 5 over n. Now what we're going to do is we're going to kind of expand this portion out. We're going to distribute the 2's. So we now get the limit as n approaches infinity of 5 over n times by 2n plus -2 plus 2 times by 1 times by 5 over n minus 2, apparently I forgot a 2 there, plus 2 times by 5 over n plus ... 2, or sorry, not plus, but yeah, plus ... minus 2. Kind of got skipped there. Sorry. There we go. back here we are. Negative 2 plus 2 times by n times by 5 over n. Well, now what we have here is we can distribute this, we can multiply, we're adding this negative 2 n times. So this really is saying negative 2 times by n, but we also have the 2n. So this limit just got a whole lot nicer of 5 over n times by, well, we have 2n minus 2n, because we're multiplying this negative 2 by n times, which is just going to become 0n. But now what we're going to do is we're going to think of a sum. We're going to try rewriting this entire expression as a sum. And we can. In fact, what I'm going to do here is I'm going to say 2 times by, and inside of all of these, we're just going to factor out a 5 over n. And now we're going to write this as the sum from I is equal to 1, because we started count with 1, 2, 3, and we go to n of I. Alright, now what we have to do is we're just going to take the limit as n approaches infinity of 5 over n times by 10 divided by n. Well, the cool thing about this is we know what this value is equal to. The summation from I is equal to 1 to n, that is the same thing as I plus 1, n times by n plus 1 divided by 2. Well, we can now distribute this 5 over n, and we now get the limit as n approaches infinity of 25. These two, this n and this n will cancel, so we are left with 25 divided by n times by n plus 1. Well, as n goes to infinity, this is just going to slowly start to look like 25n divided by n. And as n approaches infinity, well, these two n's will eventually cancel each other off, so we know this limit's going to approach 25. And that would be our solution to the definite integral. And I was going to work this problem here, but I'm going to actually leave that problem for you, and I'm going to leave the answer in the comments. The last thing that I want to do today is talk about some of the properties of the definite integral. So if b is greater than a, then the integral from b to a of f of x dx is equal to the integral from a to b of f of x dx. And the reason for this is, let's say we're taking, so in this case, we're minusing a minus b and dividing that by n. This expression is negative because b is greater than a. However, it's going to have the same value as b minus a divided by n. But this is going to be positive. So we can swap the bounds of integration and make the integral negative, so our dx is positive. Alright, well, another few integral things that we should know is the integral from a to a of f of x dx is equal to 0. And the reason for that is, let's say we're looking at the curve right here, and we have this point right here. It's a. Well, we're just integrating a point. It has an infinitely small width, as thus it has an infinitely small area. For property number 3, the integral from a to b of c times by dx is equal to c times by b minus a. I did not know that had a highlighter function yet, but anyway. Let's look at a function. Let's say it has a height c. Well, if we take this across, and let's say we have the point A and a point B, it's going to have a height of c, but the width of this interval is going to be b minus a. So this area is going to be c times by b minus a. All right. For the property number 4, the integral from a to b of f of x plus or minus g of x dx is equal to the integral of a to b of f of x dx plus or minus the integral from a to b of g of x dx. So a good example of this is, let's say that we have an expression, and it is, let's draw out two curves real quickly. Alright, so we have right here, let's call this A. This is function A, and this right here, let's just make it a straight line, is function B. If we add A and B together, we're going to get a function that somewhat looks like this. Well, the area of these two curves added together is going to be the same area under here. I hope this diagram kind of helps explain it. For the integral of a to b of c times by f of x dx is equal to c times by a to b of f of x dx, that's kind of, you're vertically stretching the function. So each of the y values are going to be multiplied by that. So we can factor out that c from all the y values whenever adding up the sum. So if f is even, then the integral from negative a to a of f of x dx is equal to 2 times by the integral from 0 to a of f of x dx. Think of a parabola here, just a parent function parabola, and it opens upward. Well, no matter what way we slice it, if we call this negative a and this a, the area between the two is going to be the exact same. So we can just evaluate it from 0 to a of f of x and multiply that by 2. And if f of x is odd, then the integral from negative a to a of f of x is 0. And I suppose a good example of this is the function y is equal to x cubed. So the reason for that is the integral from a to negative a is going to have the same area under the curve, except for over here it's negative. So I have actually neglected to talk about what the integral actually represents. So whenever we're looking at negative values of f of x, the height of these rectangles are going to be negative. So whenever we're adding up these areas, we're going to get a whole bunch of negative areas. Now the issue with that is, according to the actual definition of area, the area cannot be negative. Area can't be negative. It would be unreasonable. I don't have any other way of describing it. But we have functions that go beneath the x-axis. So the way that we actually, or what the integral really represents, is the net change. It isn't particularly just it isn't the area. It is the net change. In some circumstances, it can be the area. Let's say that we take the integral from a to b. This is the area. But if we take the area from a to c here, this is the net change because we have this negative area. So if we want the actual area, then the area under, or the area of this curve is going to be this area above the curve minus this value under the curve, the area under the curve. So this is going to give us the actual area that the curve bounds between the x-axis. I hope this is kind of making sense for you. So really, this idea of the definite integral, to sum it up, is not the area under the curve. It is, however, the net change of a function. It is the net area, really, to sum it up. It is the net area. It's the amount of positive area we have. The definite integral is the net area from A to B. If you want the exact area, you have to the exact area. It's the area above the curve minus the values of area beneath the curve, so you'll get positive. If you want the net area, it's the integral from A to B of f of x dx. I hope this has helped you all today, and if you did find this video informative, please like and subscribe.